We would be proving this inequality that for any two complex numbers, modulus of z1 positive z2 is less than equal to modulus of z1 positive modulus of z2. Now, foremost, what I'm going to do is I'm going to be considering modulus of z1 positive modulus of z2 and raised to the power 2. Now, you got to know that there is a property. The square of the modulus of a complex number is equal to a complex number multiplied by its conjugate. Okay, this can be easily proved. And since we know this property, right, I can rewrite this to be as the complex number present inside the modulus z1 plus z2, okay, that multiplied with its conjugate z1 plus z2. We got to draw the line. Okay, now you have to understand that the conjugate of a sum of complex numbers is equal to sum of the conjugates, that is z1 conjugate added with z2 conjugate. This is another property. This property can also be proved. Okay, so just remember these properties. Now, because of this fact, I can rewrite this to be as z1 plus z2 multiplied by z1 conjugate added with z2 conjugate. Now I'm going to remove the parenthesis, so I'm going to multiply z1 with z1 bar, z1 with z1 bar, plus z1 with z2 bar, z1 with z2 bar, plus z2 with z1 bar, plus z2 with z2 bar. So I've got this. Now you have to understand the next property. Now z1 multiplied with z1 bar, or in other words, a complex number multiplied with its conjugate, will give us modulus of the conjugate squared. Okay, so the same property. Okay, have that in mind. Z multiplied with z bar is equal to modulus of z raised to the power 2. Now, using this property which we have just studied, this can be rewritten as modulus of z1 squared added with, I'm not going to touch anything with this, I'm just going to retain it, z1 multiplied with z2 bar, plus I'm just going to be retaining this as it is, z2 with z1 bar, plus this is actually z2 multiplied with z2 bar, so this is going to be z2 raised to the power 2. So this is what I have got. Okay, so all of these things are obtained from this quantity z1 plus z2 raised to the power 2. So I have that in mind. Now I'm going to rewrite this quantity. So this is equal to modulus of z1 squared plus z1 z2 bar, plus I'm going to start with z1 bar and then place z2, followed by modulus of z2 squared. Okay, now there is another important property, which is you take a conjugate of a complex number and then again you apply the conjugate for the complex number, you get the complex number back. Okay, so this is a very important property you have to know, so have that in mind. I'm going to be using that. Now before I could use it, I'm going to rewrite this as modulus of z1 squared positive z1 plus z2 with the conjugate on, positive z1 z2. I'm going to place a conjugate for this and then I'm going to apply the conjugate. So if you were to see only this quantity, it has a conjugate and I'm applying the conjugate again. So when I do that, it is actually z2, because we know that the conjugate of a complex number undergoing the conjugation again will give me the complex number in its original form. So because of this fact, I am getting this quantity. I'm able to represent z1 bar times z2 as z1 times z2 bar with the conjugate, complete conjugation of this quantity, followed by modulus of z2 raised to the power 2. Okay, so this is a nice way to represent the initial quantity that we started with. Now you have to know that a complex number added with its conjugate is equal to 2 times the real part of the complex number z. Now let me take a complex number, say z is equal to some x positive iy, okay, and let me take z bar, which is going to be x negative iy. Okay, now therefore if I were to add z with z bar, I would be getting x positive iy added with x negative iy, which is going to be x positive x, adding the real part positive. Now I got a iy there and a negative iy, so both these things would get cancelled, giving me 2 times x. So z added with z bar gives me 2 times x. Now consider 2 times the real part of z. So what is that? It's going to be 2 times of the real part of z. I've taken z to be as x positive iy, so the real part is going to be x, so that's going to be 2 times x. Now if I were to take this as 1 and I were to take this as 2, comparing 1 and 2, clearly we see that this implies from 1 and 2, z added with z bar is equal to 2 times the real part of z. Okay, so have that in mind. So I would be using this property now. So because of this property, I would be able to reduce the outcome. See, actually we have got this. This is going to be modulus of z1 squared positive z1 z2 with a conjugate on positive z1 z2 conjugate on, but I need to take the entire conjugate, of course, followed by modulus of z2 squared. Now because of this fact, z added with its conjugate gives me 2 times of real z, so I'm going to be using that property which I've just proved here over here. So this is actually, consider this as a complex number. It's just one big complex number. What am I doing here? I'm taking that complex number with its conjugate, so I'm adding the complex number to its conjugate, and that is going to give me 2 times real part of that complex number. So rewriting that, I would be getting modulus of z1 squared positive 2 times real part of this complex number, which is z1 times z2 bar, followed by modulus of z2 squared. So this is what I've got. Now there is another important property you have to know. Now since this is the important property, real part of z is always less than and equal to its modulus. Okay, real part of z is always less than or equal to its modulus. So this is a very important property. Now since this is true, this is a property, you got to know this property. Because of the truth of this property, real part of z is less than equal to modulus of z, I'm going to rewrite this to be as less than equal to modulus of z1 squared positive 2 times modulus of this complex number z1 multiplied with z2. It's a complex number, right? So place that complex number, following it up with modulus of z2 squared. So we have got this beautiful outcome. Now there is another property you have to know. Now since modulus of z1, 2 complex numbers product, and you take the modulus, that would always be equal to the modulus of z1 with its product, modulus of z2. So modulus of the product is equal to product of the modulus. So this is another important property. This property can also be proved. Okay, so because of this property, okay, I can now rewrite this to be as lesser than equal to modulus of z1 squared positive 2 times modulus of z1 multiplied with modulus of z2 positive modulus of z2 squared. Okay, I'm able to get this, right? This entire outcome I'm able to get it. But what is this? This is actually a positive b whole squared. So let us do that. So this is equivalent to, less than equal to, this is going to be modulus of z1. Okay, is, as I mentioned to you, this is a positive b whole squared, right? We know that a positive b whole squared is a squared positive 2ab positive b squared. So I will be using this. So using this result, this is going to be modulus of z1 positive modulus of z2, that has to be squared. So when we square this, we get the terms modulus of z1 squared positive 2 times modulus of z1 times modulus of z2 followed by modulus of z2 squared. On the left, we started with modulus of z1 positive modulus of z2 raised to the power 2. Okay, now this is what we have arrived at, removing the squares both sides. In other words, taking square root on both sides. Okay, we would subsequently rewrite this as modulus of z1 positive modulus of z2 lesser than equal to modulus of z1 positive modulus of z2. Okay, so we have arrived at the result. So hence the result is proved. Hence proved. Okay, so that completes the proof for the very important inequality.